So let's go to make a video on Biott and Savart. Okay, so this is the idea. I have some pictures that I want to show you. It has one exercise that I want you to do it, and I will change this exercise for you to do it again. And there is something else. Well, this is also the exercise. Also, this one is the continuation of the exercise. And this is something that I want you also to do it. So let's go to explain Biott and savart. I'll go to the next page to see how. So that I have from the book, and this is the good picture that I have from the book. Let me see. Oh, let me see if I can make it bigger. Well, I cannot make bigger. Oh, let me see. Okay. So this is the equation that we just studied. The same equation, yes, it's the same equation, exactly the same equation. Instead of Q, I put dDQ, and instead of B, I put the small magnetic field that is created. Instead of B, I have put B equal magnitude of B by U sub T, and I have put the product, the cross product outside of the equation to take care only of the direction. So this equation, like that the book show you, to calculate is this way. Look this, the hand. Is the rule, oh, sorry. Thank you. Sorry, I split the whole water on my table. So let me finish. So you see this hand is called the rule of the right hand. The rule of the right hand it should be the right hand, not the left hand. You take the right hand and you point your finger. This finger you point it in the direction of B, and the other fingers will point in the direction of B. So if this is the charge and this is the velocity, the lines will do like this. You see, this is the velocity. You put your hands like the picture, and the picture, your hands, the fingers of your hand will tell you how it will do the magnetic field. But you can use this equation to calculate. You can use the equation to calculate the direction of the field. So this is the problem that I want you to make. First of all, I want you to practice this exercise. You have to read it carefully. There are two charges, one positive, one negative. Two positive. One is moving in this direction. It's in your book, so you can see in your book. The other one is moving in the direction. This one is moving in the direction X. The other one is moving in the direction minus X. And what he asks you is calculate the electrical force. So this is an instantaneous picture. You make an instantaneous picture and you calculate at this exact moment what is the electrical field and what is the magnetic field. Of course, if you wait a little bit, the picture that you will see will be different, because this chart will be here, and this other chart will be here. So the distance between them will change, so the electrical field will be changed, and the magnetic field will be changed also, and the direction of the magnetic field will be changed. So this is only for this instant, the calculation just for an instantaneous distance of these two particles that are interacting. So we have to find this charge will produce an electrical field. This is the electrical field, and also will produce a magnetic field. And you can know that the magnetic field is like this. So in this point, do like this on the charge. So this magnetic field will create a magnetic force, and the magnetic force will be this charge, by B, this velocity, this one, cross B, this magnetic field, B. So you have to calculate the magnetic field first, created by this charge, and later create the force on Q1, let's say on Q1 due to this charge. So you have to calculate two forces, the electrical force and the magnetic force. And to compare, when you compare, the comparison is like this, and it's very interesting. The magnetic force is weaker, much more weaker than the electrical force, and it's weaker in this factor, V squared over C squared. To be similar to the magnetic field, you need that the particle will move at velocity near to c, to the speed of light, and in this way, if the particle is moving, if this particle is, which particle? This one or this one? Let me see. No, this one. If this one is moving with a big velocity near to c, so the electrical field and the magnetic field that they will interact, that will feel this particle, will be similar, only on this case. So I want you to do like this. I want you to remake this example. It's made in the book. And after you are clear how to do it, I want you to do this example. The same one, but with change directions. Let's say that this particle, let me see, this particle, this one, is moving up. The same problem, but this particle is moving up, and the other particle is moving, so this one is moving in this direction, I direction. So this particle is moving in this direction. For the example that I want you to solve, I want you to solve the same problem, but with the particle, let's say, called particle 1 and particle 2. So particle 1 is moving up in the j direction, and particle 2 is moving in this direction, in this direction that I cannot see, in the xi direction. So particle 1 is moving in the j direction up, and particle 2 is moving in the I direction. So I want you to calculate the force and to see how the force change if the force, maybe we can get, let me see, the electrical force, in this case, the electrical force and the magnetic force go in the same direction. In this example, you have to see if they go in the same direction, both of them. And after you do this, after you master how to do this problem, and you can do this problem, the same problem changing direction, after you do this, I want you to solve this problem. So in this video, you have see how to calculate, how to define the law of Biott-Savart, that is how to calculate the magnetic field produced by a charge in movement, and you have also have to do two problems. This problem just to practice, this one, and this conceptual problem, to be sure that you understand. So good luck and go ahead. Next page, what? Yellow page. So this is the idea. When you have a small charge dq at any point P will produce an electrical field dd What is the relation between the electrical field and dDq and this distance r? Well, the relation is that the small field that is going to create by dDq is dDq by 4 pi epsilon sub 0, and this dd, this small electrical field created by dDq, have a direction. The direction is on the line of the vector r, so it's on the line of u sub r, unitary vector u sub r. We have done this many times. Now the problem is like this. We have seen that the force that a particle of charge q will feel in a magnetic field will be v qv cross v. But we have not said how to calculate v. Of course, we have b, for example, b, and we have a particle moving with some direction, v, let's say v, and we know how to calculate. We did it many times in the video before. We know how to calculate the force on this particle, let's say the particle 1. The force on particle 1 is the charge of the particle 1 by the velocity of the particle 1 cross the vector field that is moving, is submerged in a vector field B. But we haven't said how to calculate B. B is produced by a magnet, maybe, and B is produced by something. How to calculate the magnetic field of something in a point P. This is what it says Biott is savart, and this is based not in any way that we can deduct. No, there is no way to deduct. This is just an experimental fact that is the product of the work of Biott is savart. So let's go to the next page. We'll see how good pick right this. The next page, and the next page will show you how to calculate the small electrical field produced by a small charge. So you have a small charge dDq. Let me see the electrical field to write here to see the compression. The electrical field is dDq divided by 4 pi epsilon sub 0. It's a constant, and it have the direction of the vector u sub r. So I want to find at this point P the magnetic field now produced by a charge that is moving. First things that I have to say is this is the vector velocity, that if the charge does not move relative to an observer, this is the observer, there is no magnetic field. So the small magnetic field produced at P, at this point P, so I make this vector, this is the vector R, this is the vector u sub r, and this is the vector v. You see the vector v, and the vector v have a magnitude v and have a direction, and I put the direction of the vector v like u sub t. U sub t is this vector, u sub t, in the line of the movement. So we are supposing that v is constant. It's constant in direction, it's constant in magnitude. And the reason why we are supposing that v is not accelerating is because the calculation will be completely different in this case, and Biott is savart have to take care that when a charge is accelerating, it will radiate energy. So the electrical field will be different. So from the moment, let's go to say that the charge is moving with a vector velocity, dDq. So what said Biott and savart? Look and enjoy this comparison. Instead of the dDq for the magnetic field, for the creation of the magnetic field at this point P, instead of dDq, we have this quantity, dDq by v. So let's put it only the magnitude of p, only the magnitude of p. So let me take the vector here out, the vector here out. So dDq by the magnitude of p, okay? By the magnitude of p. So it looks the same like this, but now the source in the electrical field are the charge. Now the source is charged with movement because have velocity, dDq by p. Oh, sorry, here is r squared, of course, divided by a constant. The constants in magnetic field is called, instead of 1 over pi epsilon, 1 over 4 pi epsilon 0, is mu sub 0 over 4 pi. It's for some reason that you will see when we study Ampere law. So mu sub 0 over 4 pi. So for the moment, the magnetic field looks in the structure very similar because it has a constant. Also here we have a constant, 1 over 4 pi epsilon 0. It has the source, that is the charge for the electrical field. It has the source that is charged with movement, dDq by b. It has the r square, oh, the same like this, r square. I'm going to calculate the magnetic field at this point, and the magnetic field will depend on the distance. Big distance, lower intensity of magnetic field. But the difference here is that the magnetic field will depend on the direction of where is the point and how is moving the particle respect to the point. It will depend on this theta, of this angle. How it will depend? It will depend on this u sub t, what it is? U sub t here, in this direction, u sub t cross u sub r. So the vector b, it will not go in this direction. No, it will go in the direction of u sub t cross u sub r. So u sub t go in this direction, like the b, and I'm looking at this position p, so u sub r will go in this direction, and u sub t cross u sub r, you rotate u sub t but u sub r, and this is going to your eyes. So the magnetic field at this point is going here like this, going to your eyes. So the way to think about this is to put your finger here, I can go to the picture, that is easier. Magnetic lines will do. Around this cone, the value of the magnetic field will be like this, like this, like this, and the same magnitude. Around a circle of radius r, the magnetic field will have the tangent line of the line, and it will go all, if you calculate at this point, the magnetic field will point out like this, B, going there, if you calculate at this point, okay? So let me go to question like I write, dDV, this is the magnitude of the vector, mu sub 0 over 4 pi dDq by the magnitude of B divided by r squared. This is the magnitude of the vector, and the direction of the vector is u sub t cross u sub r. Okay, u sub t cross u sub r, this vector here. Okay, so this is the magnitude, and this is the direction. So you have to imagine how it will, what direction will take dDV at any point. At any point will change dDV, because if you are here, now u sub r has changed. U sub r is like this, and u sub t have not changed in this case, have not changed. But u sub r have changed, so you have to calculate u sub t cross u sub r. So you have this page on this